Hey y'all, I'm hoping that all of y'all are doing well and that you're adjusting to this time that we're spending at home. I wanted to take some time today to go through a topic that was on your first Learning from Home packet. It's the relative and absolute age of the Earth. It can be a little bit confusing, so I'm hoping that going through this is going to be helpful. So how do we know how old the Earth is? How can scientists know the age of the Earth? There are actually two ways that we use, two things that you guys need to be familiar with. The first one is called relative dating or relative age. The second one is called absolute age. So like I said, we're going to start out with relative dating. Relative dating simply places events in sequence by comparing to other events. So you're going to use statements like this thing is older than this other thing, or it's younger than, or the same age as. You're simply just putting things in order. You're not giving them an exact age or an exact number. You're just saying what's older, what's younger by comparison. There are a few laws that you need to understand when we talk about relative age and relative dating. The first one is the law of original horizontality. All this is saying is that when sedimentary rocks are laid down, when they're formed, they are originally laid down flat. So they're going to be in flat layers. So that tells us if they're not in a flat layer, something has happened. Okay, so original horizontality is simply that sedimentary rocks are originally laid down flat. The next law is the law of superposition. This tells us that the oldest rocks are on the bottom and the youngest rocks are on the top. That might seem kind of like a duh type situation, but it is a law that goes along with this, and it is one that you need to be familiar with. So the oldest rocks are on the bottom and the youngest rocks are on the top. As long as everything is still flat, nothing's been disturbed, we can know the youngest rocks are at the top, the oldest rocks are at the bottom. And this happens, we know this because as rock layers are deposited, they're deposited from the bottom up. So as we go back in time, as we dig deeper, we're going farther back in time. And the farther back in time we go, the different organisms that we're going to find are going to be are definitely going to be different. So you can see in this picture at the top, in the Cenozoic era, which is the era that we're currently living in, you find fossils of modern mammals, of monkeys and apes, and early mammals. As you go further back and you go further down, like into the Mesozoic era, that's where you're going to find your dinosaur fossils. And then even further beyond that, in this bottom layer, the Paleozoic era, which is even earlier in time, that's where you find things like amphibians and fish and invertebrates. So those really early organisms are going to be found down at the very bottom. The next law is the one where it starts to get a little bit tricky. This is the law of cross-cutting relationships. So this says that the rocks which cut across other rocks are younger than the rocks they cut across. So all that's saying is, for example, if you look at if you look over here at this example right here, okay, the oldest rock is at the bottom because these three layers are flat and they've not been bent or anything like that. So these three layers were laid down first. Then this guy, number 4, came and cut across those three layers. But notice how he stops, how number 4 stops at the top of layer 3. So we know that this fault or intrusion or whatever it may be is actually older than this top layer. This top layer, number 5, is the youngest because it's not intruded upon by number 4. Okay? Now, if we look down here at the bottom, Okay, we've got this limestone and siltstone, and then the fault has cut through those two layers, and then the basalt was laid down. So the basalt is actually the youngest item here, and then the fault, then the siltstone, and the limestone is the oldest. Okay, and then over here on the right, you've got this layer A down here, this kind of burgundy colored layer down here at the bottom. That's going to be your oldest layer. And then this crack that goes through here, this is your youngest item on this diagram. And we know it's the youngest because it cuts through everything. It cuts through C, cuts through D, B, and A. Okay? So that was relative dating or relative age. Now let's talk a little bit about absolute dating or absolute age. This one, you're actually assigning an actual age or an actual number to an object or to something. So whether it's an object, an event, a rock, you're determining the actual age in numbers of years of this thing. And how do we do that? Well, we do that a couple of ways. One way is using index fossils. Another way is using something called radioactive isotopes. And an isotope is simply an atom of the same element that has a different number of neutrons. And we'll get into that in a little bit. Index fossils are fossil remains of an organism that lived in a particular geologic age, and they're used to identify or date the rock in which they are found. So we know certain index fossils were only alive during a very particular time. So we know that if we find that index fossil, we can say, okay, this rock is from this particular geologic age. So we are able to give it a date based on when we know that index fossil was alive. Radioactive isotopes, again, they're isotopes. Isotopes are just the atom of the same element with a different number of neutrons, and they are unstable, and they break down into other stable isotopes by this process called radioactive decay. So over time they go from being unstable to stable, and this decay is actually, we know how long it takes for certain isotopes. The radioactive isotope is called the parent isotope, and the stable isotope that's formed by the breakdown of the radioactive is called the daughter isotope. So in all of these examples that we're going to be using in a little bit, you'll see the green balls are going to be the unstable parent, the purple balls are going to be the stable daughter. Okay, so just keep that in mind as we go through some of these examples. So like I said, we know the rate at which these radioactive isotopes, and that rate is called half-life. So half-life is the time needed for half of a sample of a radioactive element to undergo radioactive decay and form daughter isotopes. So in the example down here at the bottom, the half-life is 100,000 years. If you notice here in this on the left, the whole entire sample is parent isotope. Well, after 100,000 years, only half of that sample is daughter isotope, or is parent isotope. Half of it has already decayed to daughter isotopes. So half of what is left, okay, so we've got 8 parent isotopes here. After another 100,000 years, we have 4. So we have half of what was remaining, okay? So that's the key. You've got to remember it's half of whatever is remaining. So half of this original sample after the first 100,000 years, half of what was left is what's left after another 100,000 years. So scientists use lots of different radioactive elements that have different half-lives. We have things like carbon-14, uranium, lead, and argon. These are all different radioactive elements that we're able to use for our radiometric dating or our absolute dating. If you're trying to date something that's fairly young, so thousands of years old, or something that was once alive, you're going to use carbon-14. So carbon-14 has a relatively short half-life of 5,730 years. And I say relatively short because we're talking about the span of the history of the Earth. We know that the Earth is 4.6 billion years old. So in the grand scheme of things, that 5,730 years is relatively short. So something that's fairly young or something that was once alive you're gonna use carbon-14. If you're trying to date something that's a lot older, say some rocks that are millions or billions of years old, you're going to want an element with a long half-life. So for example, uranium-238 has a half-life of 4.5 billion years. So that's really long. So let's just take a look at a couple of practice problems real quick. Here's how you're going to do this. This practice number 1 says calculate the age of this sample if the half-life of purple and green volume is 10,000 years. So you have to look at the number of parent isotopes and divide it by the total number of isotopes. Well, if we look at this sample here, our total number of isotopes is going to be 16. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 16 is our total number. Our number of parent isotopes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12 divided by 16, and then if you multiply that by 100 to give yourself a percentage, you end up with 75%. So 75% of our sample is still parent isotopes. So we can then take a look at our graph to figure out how many half-lives we've been through. Okay, so real quick, let me remind myself. Our half-life of this was, oh, it's not letting me go back. Okay, so anyways, we have 75%. So 75%, you find that on the percentage of parent isotope remaining. So 75%, you go over to where it hits this red line, and this line is what we're looking for. And that is 0.5 half-lives. So then you multiply 0.5 times the 10,000 years, that's the half-life of the sample, or of the isotope, excuse me, and you end up with 5,000 years. So our sample is 5,000 years old. Okay, so if we calculate the age of this sample, if the half-life of green and purple spherium is 1 million years. So again, you've got to look at the number of parent isotopes remaining divided by the total number. So again, total number is 16, and we have 4 parent isotopes remaining. So 4 divided by 16 times 100 to give yourself a percentage, that's going to be 25%. So 25%, you find that on the graph. You go over to where that meets the line, and that's right here at 2 half-lives, okay? So if our half-life is 1 million years old, we multiply that by 2 half-lives, and that gives us 2 million years, okay? So that's all I have for you as far as the relative and absolute age, and I hope that it was helpful in some way, and again, that I hope you guys are doing well in this time, and that you're able to spend some time with your family, as well as continue to do some of your schoolwork. All right, I will talk to you guys later. Have a good one.